Picture Earth with something like a nervous system. Tiny sensors in forests, oceans, farms, cities, and machines, detecting change as it happens. In this project, TinyML turns local signals into global awareness for planetary resilience. So far, we've moved from autonomous AI societies and spatial intelligence into bio-AI, robotics, advanced materials, climate repair, and neuromorphic edge cognition. Project 27 takes the next step, extending intelligence outward into a planetary sensing layer that helps Earth observe, interpret, and respond to change in real time. At the heart of this idea is a shift from delayed reporting to continuous awareness. Instead of learning about damage after it occurs, tiny sensors listen locally, in forests, oceans, farms, bridges, pipelines, and cities. Small AI models interpret signals like heat, vibration, moisture, sound, pollution, or movement. Together, they form a sensory mesh that can spot stress early and turn environmental change into real-time situational awareness. Planetary sensing cannot depend on every sensor streaming raw data to the cloud. That approach burns bandwidth, adds latency, and breaks down when power or connectivity is unreliable. TinyML changes the flow. A small model runs directly on the device, filtering noise, recognizing patterns, and flagging rare events as they happen. Most data stays local. Only useful insight, such as an anomaly, fire signal, or animal detection, needs to be sent. That makes sensing networks cheaper, more private, more resilient, and scalable enough for global environmental monitoring. The sensory planet begins with physical contact with the world. Sensors act as the translation layer between real conditions and digital intelligence. Some measure ecological signals such as temperature, soil chemistry, air quality, water chemistry, radiation, and biodiversity. Others watch infrastructure, detecting vibration, strain, corrosion, pressure, leaks, and fatigue before failure becomes visible. Bioacoustic and vision systems add another layer, recognizing animal movement, chainsaws, pests, disease vectors, or habitat disruption. These interfaces can live almost anywhere: buoys, trees, roads, pipes, buildings, drones, satellites, or machines. TinyML turns that distributed hardware into a responsive sensing mesh. For this mesh to work, data has to move through very different environments. In dense regions, low-power, wide-area networks can collect small event packets from thousands of sensors without draining batteries. When a sensor cannot reach a gateway directly, mesh networking lets nearby nodes relay the signal, keeping coverage resilient during fires, storms, or infrastructure failures. For oceans, polar zones, forests, and remote farms, satellite backhaul carries anomaly alerts to regional edge systems and global models. Over time, 6G edge corridors could add faster, lower latency paths for high-density sensing, and rapid model updates. This is where sensing becomes understanding. A device may notice a heat spike, unusual vibration, sudden soil dryness, or a collapse in birdsong, and flag it immediately at the edge. But the deeper intelligence comes from context. Regional models compare that local event with nearby sensors, land use, infrastructure, ecology, and expected seasonal behavior. Broader models then ask whether the pattern matches larger watershed, climate, or planetary trends. This layered approach helps separate noise from meaningful change, so alerts become evidence, not just raw data. Trustworthy sensory systems need more than access to data. They need evidence. A sensor event should carry a device signature, location, timestamp, and measurement context. Gateways can turn that event into hashes or proofs, then publish it through open protocols, so agencies, researchers, startups, and civic platforms can use the same facts. Decentralized ledgers do not need to store all raw data. They can store proofs, permissions, provenance, and incentive records. That makes manipulation harder in climate reporting, disaster response, carbon markets, public health, and infrastructure monitoring. One useful way to see the system is as a pipeline from noise to usable awareness. Sensors first measure continuously: water chemistry, air quality, soil moisture, temperature, and movement. TinyML then infers locally, converting raw streams into compact signals like events, features, confidence scores, and anomaly alerts. Routine data is filtered out, so networks are not flooded. Regional models aggregate many local alerts, such as a river chemical anomaly confirmed by 43 sensors. Finally, global digital twins simulate the larger picture, helping leaders see planetary health trends and choose better interventions. A planetary digital twin is a live model connected to the real world. Sensors in forests, watersheds, grids, roads, farms, and coastlines stream signals into a digital version of those systems. The model can track water stress, air quality, biodiversity, grid risk, or wildfire probability as conditions change. Its real power is simulation. Before building a seawall, changing irrigation rules, or rerouting energy, decision makers can test likely effects. The twin becomes a shared evidence space where governments, scientists, communities, insurers, and planners work from the same evolving picture. Now imagine the Amazon Basin early stress network in 2040. Tree-mounted sensors hear chainsaws, drying canopies, insect outbreaks, and shifts in birdsong before satellite images show damage. River and coastal sensors track warming, acidity, plastics, and fish movement. Along wildlife corridors, cameras, motion sensors, bioacoustics, and environmental DNA confirm whether species are still moving safely. The big shift is timing. Conservation teams stop waiting for after-the-fact reports and start responding to living ecosystems in near real time. The planetary sensory mesh also becomes highly practical in the built environment. Bridges, tunnels, pipelines, and grids can report strain, leaks, vibration, or overload risk before small faults become public emergencies. The same sensing layer helps cities track heat, flooding, air quality, traffic pressure, and safety hazards in real time. Industrial equipment joins in too, flagging degradation before failure. The result is not just more data. It is infrastructure that can warn, prioritize, and coordinate repair before disruption spreads. The power of a sensory planet becomes clearest when signals are connected across systems. Water data can expose contamination, drought, salinity intrusion, groundwater loss, and flood risk. Farm sensors add soil moisture, nutrients, crop disease, pests, and local heat stress. Health monitoring adds wastewater signals, air pollutants, vector habitats, and conditions that favor outbreaks. Climate models then stop relying only on distant averages. They receive continuous ground truth from real places, making risk forecasts more local, earlier, and more actionable. The key mental model is interdependence. Climate affects water, water affects food, and all three shape health. By 2050, the sensory planet could move us from scattered monitoring to coordinated planetary stewardship. Ecological health, water stress, disease signals, infrastructure risks, pollution, and climate volatility become continuously visible. That visibility changes decision-making. Disasters can be anticipated earlier, adaptation can be guided locally, and critical systems can be managed together rather than repaired after failure. Project 27 gives us the sensory planet, a distributed mesh that detects stress, change, risk, and opportunity in near real time. TinyML keeps it scalable by acting locally, while verified data and digital twins turn signals into trusted intelligence. Next, we move from sensing the planet to coordinating action through autonomous machines, decentralized science, and resilient simulation.